These are the practice problems for lesson 15. In this first problem, it says, if you have a triangle that has a 40-degree angle, then draw an isosceles triangle with a 40-degree angle. I can think of two ways to do that. One is to make the 40-degree angle one of two equal angles in the isosceles triangle. That means 100 degrees is left over. Each of these sides will be equal length, and this is 40 degrees, 40 degrees, and 100 degrees. The other way I can think of doing it is make the 40-degree angle the angle that is not equal. And so that leaves 140 degrees. Divide that 140 divided by 2, 70 degrees for each of these angles because it's an isosceles triangle. So an isosceles triangle has two equal angles and two equal sides. Then it says, make a right triangle with a 40-degree angle. So I can only think of one way to do that, because if this angle is 90 degrees and this angle has to be 40 degrees, that forces that third angle to be 50 degrees. It cannot be anything else. And this goes back to a lesson we had earlier where for two triangles to be similar, the minimum that you need are two angles to be congruent. Once you have two angles that are congruent, it forces that third angle to be a certain size. In this case, it's 50 degrees. So whatever you do, if you have an angle that's 90 degrees and an angle that's 40 degrees in a triangle, that third angle will be forced to be 50 degrees because remember, the angles of a triangle have to add to 180 degrees. So if you try to flip it around, rotate it, try to change it in any way, you're still going to end up with triangles that are similar. So 40 degrees, 90 degrees forces this angle to be 50 degrees. And so just to prove that, if you take a similar triangle through a series of transformations, you can prove that it's either similar or congruent. And so if I rotate this around and I can reflect it, prove that these two triangles are in fact, actually in this case, congruent triangles. All right, problem number 2, you're given measures of the angles of a triangle and asked, can they actually form a triangle? Well, A, you can. They add up to 180 degrees. That's an equilateral triangle, 60 degrees, 60 degrees, and 60 degrees. It's right here. It can't be anything else. It has to be an equilateral triangle. They can be similar, they can be different sizes, but they have to have an equal length sides and equal angles. B adds to more than 180 degrees, so you cannot make a triangle out of that. C adds to less than 180 degrees, so you cannot make a triangle out of that. D is 90, 45, and 45. So this is an isosceles right triangle. 90 degrees is the right angle, and the other two angles are 45 degrees, so it's this one right here. It has to be an isosceles right triangle. Can't be anything else, because these two angles have to be 45 degrees. This angle is 90 degrees. And the last one is an isosceles obtuse triangle. It's an angle greater than 90 degrees, but two of the angles are equal. That means that two of the sides are equal. So yes for D, yes for E, and yes for A. Okay, the next problem says that if you have a triangle with an angle that is obtuse, can angle B or C, the other two angles, also be obtuse? And the answer is no, they can't. Once you have an angle that's greater than 90 degrees, the other two angles have to add to less than 90 degrees. So neither of those angles can be greater than 90 degrees, neither can be obtuse. But let's look at a couple of examples. If I make a triangle, I'm going to just move this closer and see if I actually can get it to be 90 degrees. And as it gets closer and closer and closer, this angle is getting larger, but it will never reach 90 degrees. It cannot. So right here you have a really tiny angle up here, and this is the angle that's greater than 90 degrees. This angle is approaching 90 degrees, but it will never reach it. It will never equal 90 degrees. And so I colored the angle in a little bit so you can see a little bit better. As this side gets shorter, what happens is this angle gets larger and larger and larger. We've had that before. And this angle up here gets smaller and smaller and smaller because these two angles have to add to the remaining amount. And that's less than 90 degrees because this angle is greater than 90 degrees. So it goes shorter and shorter and shorter. That angle is getting larger and larger and larger. So let's zoom in a little bit. But it will never reach 90 degrees. This is a really skinny triangle here. This angle is greater than 90 degrees, but this angle will not reach 90 degrees. And this is a really, really, really tiny angle up here. Now what happens if we do the same thing with an angle that's less than 90 degrees? Can this angle out here reach 90 degrees? And the answer, of course, is yes, it can. Because here's 90 degrees, this angle is less than 90 degrees. So this angle plus this angle up here, which is going to be really tiny, have to add to the other 90 degrees. But yeah, you can have an angle that's 90 degrees if your beginning angle is less than 90 degrees. So if this is 90 degrees, for example, and this is 85 up here, this has to be 5 degrees. Small size. All right, problem number 4 gives you 3 different pairs of figures and asks you to describe a transformation that takes figure A to figure B, or polygon A to polygon B. The first one, this is a translation. So you can think of it as just moving along this angle here, but let's describe it a little bit better. So for every unit that each of these points moves down along a y-axis, we're going to move 2 units to the right along the x-axis. So down 1 unit to the right 2 units, down 1 unit to the right 2 units. And to get from this figure, this polygon, to this polygon, you have to do that 3 times. So if you do it in one step, it's going to be 3 times this 1 unit, 1, 2, 3, and 3 times this 2 units, 1, 2, 3, 3 times 2 is 6 units. So this is down 3 units and to the right 6 units, 1, 2, 3, 4, 5, 6. So translation, the pink, move in one step at an angle. And the blue, for every 1 unit that you move down along the y-axis, you move 2 units to the right along the x-axis. 1 unit down, 2 units to the right. And eventually you'll get to this polygon. The red is doing it, showing the move, vertical move and horizontal move in one step. So 3 units along the y-axis and 6 units along the x-axis. All right, the second pair of figures. These are reflections. This is a reflection. And you can see that the line of reflection is right here. It's midway between these 2 corresponding points, and it's at a perpendicular angle, or a 90-degree angle. So you're going to move from this point to this point, an equal distance on each side, at a perpendicular, in a perpendicular direction. In other words, at a right angle. So the same is true for up here. The same is true for these corresponding points, and the same is true for these corresponding points. So a line of reflection is the midpoint between the corresponding points at a right angle. It's perpendicular, forms a 90-degree angle. So you move to the line of reflection at a right angle, and then you move an equal distance on the other side, and you're going to get to the corresponding points. So this is not a rotation. Remember, if it's a 180-degree rotation, so if you imagine that you're going to rotate this over here 180 degrees, this line is also going to rotate 180 degrees, or the side, actually, it's going to rotate 180 degrees up here. It's going to be on the wrong side. Over here, it's down here, but if you rotate it 180 degrees, it's going to be up here. It's going to be on the wrong side, so it's not a rotation. And likewise, this side will rotate down here. It's also going to be on the wrong side. It's rotating from here to here. So it is not a rotation. It is a reflection. This one is a rotation, and it's a 90-degree rotation. You can see that this point here is going to rotate 90 degrees. If I drew a line straight down here and over here, that's a 90-degree rotation. And you can do this several different ways, and we've done it several different ways throughout these lessons. I think the way that shows it the best, there's the 90 degrees. So you go to this point and you go down here to this point. So if you count out 1, 2, 3.5, then you count down. So rotate 90 degrees and count down. There's the half, 1, 2, 3. You can do that for every point, just figure it out by counting. But I think visually, it's nice to show the circles and the rotation because these are rotations. So it's nice to show that movement. So that's a center of rotation. It's a 90-degree rotation. And it's counterclockwise. It's going the opposite direction of a clock. And so there's a circle for these 2 points. There's the 90-degree rotation. And there's a circle for those 2 points. And this is another 90-degree rotation. And that's the circle. I need to add a circle for that point. So now if we keep this image on those 3 points as it rotates around. So this point, and this point, and this point, you're going to see that it stays on those 3 points and rotates around 90 degrees to here, like that. So it is a 90-degree rotation. All right. So the last problem, it says, draw a scaled copy of this quadrilateral. A quadrilateral is a 4-sided image. Quad means 4, lateral means side. So a quadrilateral. ABCD using a scale factor of 1/2. So that means that the length across the diagonals is going to be half the length. So if this is 1, 2, 3, 4, 5, 6, this length for a scale figure of 1/2 is going to be 3 units. This length is 1, 2, 3, 4, 5, 6. So this length is going to be half, or 3 units. This length is going to be half, or 1 diagonal. This length is going to be half. It's right there. And this length is going to be half, which is right there. And so you can draw those diagonals and then connect the points that are halfway. So this is 1/2 of this length. This is 1/2 of this length. So it's half the distance from here to here, half the distance from here to here, and half this distance from here to here. So put a point here, point here, point here, and point here. So this is a quadrilateral that has a scale of 1/2 the original quadrilateral. And I also did one that has a scale of 3/2, so you can just see it. If you move out from this center point right here, if you move out, let's go this way. If this is 1/2, this is the whole thing, and this is another half, so this is 3/2. If you go up this way, this is 1/2, this is the whole unit. This is 3/2. This is 1/2, 2/2, 3/2. Let's say it that way. This is 1/2. So counting 2 units. This is 2/2. This is 3/2. And down this way, this is 1/2. This is 2/2. So the whole length, which is equal to 1, and 3/2. You just have to look at it for a while and think about it. It says the vertices of scaled copies will fall on the diagonals. So I drew this quadrilateral, drew the diagonals, and so the vertices of the scaled copies will fall on those same diagonals. So go 1/2 the way, or 3/2 the way. Scale factor of blue is equal to 1/2, and a scale factor of pink is equal to 3/2. So the pink is each length is 3/2 the size of the original figure, which is in black. And the blue figure, the scale factor is 1/2. So each length is 1/2 the size of the original figure, which again is the black image. Just have to work with it, practice with it. All right, so practice problems for lesson 15.